Virtual Touch. The team is conformed of Oscar Bollet, Ryan Borns, and Luis Macias. Our advisor is Michael Fu. The project is for EECS 398 Engineering Projects 1 and EECS 399 Engineering Projects 2 during the spring 2020 semester.
The goal of this project is to create a device that, through surface stimulation of the hands, provides a touch-like feedback on VR interactions.
The problem we're facing with the current UECU unit, which you can see here, is that it is not portable. This needs to be connected to a computer, and for us to interact with it in virtual reality, the headset needs to be connected to a computer too. So what we're trying to do here is create a circuit that enables us to control stimulation with the headset and make all of this mobile. The way we're gonna approach this is using Bluetooth, a mobile headset, which is the Oculus Quest, and our own circuit. The UECU will become more mobile because we will add a Bluetooth module that will instruct the UECU where and how to stimulate. It will also become more adaptable because it will increase from 4 outputs to 16. That will allow us to have more configurations in the hand using different sizes of electrodes that will generate different kinds of stimulations. Our current competition is the bulky Tesla glove. It's a huge glove that basically allows you to feel just like we do, but it's too big. Other different technologies like the pneumatic actuators just make you feel pressure by inflating a little bag, but they don't have the same feeling of natural sensation. For stimulating nerves, we need to create a potential across the nerve endings in the axon. To do this, we normally just insert 2 electrodes into the skin, and then we run a current through them, and that current generates a field. But in our case, we don't want to have an invasive approach, so we use surface stimulation. But since we're using surface stimulation, distance has a much greater effect.
During the design phase of this project, we came across a number of constraints that were imposed upon our system. The first constraint was set by the IEC standard 60601, which dictated the basic safety requirements of medical-grade electrical equipment. Based on that standard, we needed to ensure that the output of our system had leakage current of no greater than 100 microamps. The second constraint is the average reaction time for tactile feedback, which is 155 milliseconds. This meant that our system had to have a delay that is no more than 155 milliseconds between a virtual interaction and the delivery of an electric stimulation. The third and final constraint imposed on the system was that whatever extension we added to the UECU unit had to be small enough to not impede the user's movement, as they had to carry the UECU on their person while using the system.
Now we're going to look at how our system works as a whole by looking at this functionality diagram we created. Our system starts with the VR headset detecting in the virtual environment which finger the user uses to pop which bubble, and then it relays this information via Bluetooth to the Arduino. And then Arduino first talks to the UECU and tells it to create the necessary signal to stimulate the user's finger. And then this signal is sent to the left hand or right hand board through channels. Channel 1, 2, 3 connects to the left hand board, and channel 4, 5, and 6 connects to the right hand board. And then Arduino talks to the left hand boards and right hand boards first registers respectively. It sends them a 24-bit signal telling them to open the gate necessary for the electrode which was going to be stimulated. This signal that the first registers receive is a serial command, and it cascades down to the second and third. And then after the necessary gate is open, the signal goes to that electrode, to that finger, and then it travels down the user's arm to their elbow, where the anodes are connected. And then from the anode, the signal goes back to the UECU, completing the whole loop. And that's how this is. Now we're going to look at our schematic and go beyond the circuitry real quick. We have our input pins here, which gets the serial command from the Arduino, and then this travels down to the registers. Each register is connected to a matrix of 8 optocouplers, and these optocouplers control the electrodes inputs that they can receive. And then in series with each optocoupler, we have a LED which lights up if the optocoupler is turned on. So if the LED is turning on or off, tells us if the electrode is receiving a signal or not. We use this as a demonstration tool. It helps with troubleshooting. And the signal after the optocouplers travel out from the output pins to the electrodes. Now we're going to look into our PCB layout.
In order to meet our success criteria of minimizing the overall board size so that the width of the PCB fits within the width of the UECU, we use entirely surface mount components to create our optocoupler matrix and shift register control units. When designing a final PCB, we ensure that it was compliant with the standard set by IPC 2152, which is what we use as our basis for our choice width so as to minimize heating. The final board dimensions were 2.65 inches wide by 1.85 inches long, which is within our width of our UECU unit, which was 30 inches wide. After finalizing the PCB design in EagleCAD, we then populated a 3D model of the board with models of the components, and we used that 3D model of the left hand, right hand, and breakout board so that we could create a 3D model of the complete circuit stack, which we could then model as being plugged into the UEC unit itself, creating a final design for a complete hardware assembly.
The Arduino right here is the brain of our board. It includes a Bluetooth module that communicates with the Bluetooth module in the headset. This then connects to our own hardware and enables us to turn on and off optocouplers, which direct the signal from the UECU. We're using an Oculus Quest. To develop a VR simulation for this headset, we need to use the Oculus integration and Unity engine. We're using these tools to create the VR environment where we perform hand tracking using the Oculus integration, and also we use 6 degrees of freedom tracking. As we can see in the background, this is how the device should be used. The person is interacting with bubbles, and she gets a feeling, a sensation on their finger, and that's how she can tell us if she touched or not the bubble.